Welcome to the Explainer. So glad you could join us. Okay, let's jump right in, because today we are looking at our drilling rig survival guide. Specifically, we're unpacking the Batch 3 formulas and key figures from our source material. Now, look, it's really easy to see a list of formulas and just zone out, right? Thinking it's just dry math. But I want us to totally shift our perspective here. We aren't just talking about equations on a page. These numbers, they are the absolutely critical boundaries that keep a drilling rig running safely. They're like the invisible guardrails for every single operation out there. They dictate what can be lifted, what can be contained, and what can go catastrophically wrong if they're ignored.
So, here's our roadmap for this explainer. Chapter 1, Gravity, Geometry, and Heavy Lifting. Chapter 2, Invisible Hazards, Gas and Pressure. Chapter 3, The One-Shot Operation, Cementing. And finally, Chapter 4, Rig Rhythms and Crucial Datums. Let's get right to it.
Section 1, Gravity, Geometry, and Heavy Lifting.
Okay, take a look at this number, 600. That is the weight, in pounds, of just a single 31-foot joint of 5-inch nominal drill pipe. The pipe itself runs about 19.5 pounds per foot. So when you realize that just one single piece of standard pipe weighs more than a massive motorcycle, it really drives home why pipe handling planning isn't about muscle, it's purely mechanical. Literally nothing on the catwalk is a two-man lift. The kind of gravity we're dealing with here demands total mechanical respect.
And, when we start stringing thousands of feet of that heavy pipe together, we really have to look up to the very top of the derrick. For derrick load calculations, the crown block is the ultimate pivot point. The whole hoisting system hangs right from it, bearing the sum of all these massive forces. So your crown load isn't just the hook load. Nope, it equals the hook load, plus the tension in the fast line running down to the drawworks, plus the tension in the dead line running over to the anchor. It's the grand total of the entire system pulling down on the rig structure.
So how do we actually manage those insane loads? Well, we use a stringing pattern, relying on what's called the reeving advantage. The formula is actually beautifully simple. N lines each carry approximately 1 divided by N of the total load. Let's say you string 12 lines between the crown and the traveling block. Each of those lines is only taking about 1/12 of the hook load. Now, once you factor in sheave friction, a 12-line string gives you roughly 81% efficiency. This drastically multiplies the lifting capacity of the Drawworks, which is exactly how standard wire rope can lift a 1,000,000-pound string without snapping.
But physics, as we know, always demands a trade-off. Let's break down this comparison. Over on the left, we've got that massive 12-line lifting capacity, but on the right is the cost. You actually have to spool 12 feet of fast line onto the Drawworks drum for every 1 foot the block actually lifts. So it's a direct balancing act between your lifting capacity and your trip speed. Basically, you are trading distance and speed for raw, shear pulling power.
This brings us to a really crucial takeaway for this first section, the universal rule of the weakest link. It doesn't matter if you're talking about a catline boom hoisting materials up to the floor or speccing out a highly complex wellhead Christmas tree. They both share the exact same logic. They are rated as an entire assembly. Think about a catline. You've got the boom, the sheave, the rope, the cathead. The system's lowest rated component sets the absolute limit for the whole operation. And, just a heads up, on a catline lift, that weak link is usually the rope.
Moving on to Section 2, Invisible Hazards, Gas and Pressure.
Seriously, if you take nothing else away from this explainer today, please remember this specific number, 1.19. That is the specific gravity of hydrogen sulfide, or H2S gas. Since everyday air has a specific gravity of 1, this perfectly illustrates that H2S is significantly heavier than air. It actually behaves a lot like water. It flows downhill and it pools in unventilated low points, specifically places like the rig cellar right beneath the floor. It is completely invisible, and it just waits exactly where you might climb in. Because of that 1.19 specific gravity, any cellar or pit entry is strictly governed by OSHA's confined space rules. You absolutely do not just climb down a ladder. First, you test the atmosphere in the space, you provide active ventilation, you monitor the air continuously, you post a dedicated attendant outside, and you establish a solid rescue plan before anyone goes in. This isn't just annoying bureaucratic paperwork. This compliance checklist is quite literally life-saving math. The physics basically guarantee that heavy gas will sink, meaning testing isn't just being cautious, it is a mathematical necessity.
Now, let's move from the cellar down into the well bore itself, where we run into the well control golden rule. If you find yourself circulating out a dangerous kick, your ultimate goal is to keep the pressure at the bottom of the hole completely constant. But how do you actually do that from all the way up on the surface? Well, you do it by holding the drill pipe pressure constant. That drill pipe is your direct hydraulic tether to the very bottom of the well. And that concept seamlessly brings us to kill sheet calculations. Let's just quickly walk through how we manage that pressure based on the source text. Starting a well kill means you need to know your initial circulating pressure, or ICP. That's just your shut-in drill pipe pressure plus your slow circulating rate pressure. Then, finishing the well kill requires knowing your final circulating pressure, or FCP. Check out the worked example here. You take your slow circulating rate pressure, let's just say it's 400 psi, and you multiply it by the ratio of your kill mud weight to your old mud weight. So 400 times 13.2 divided by 12.0 gives you exactly 440 psi. The math tells you exactly where your surface pressure gauge needs to be sitting to safely kill the well.
All right, Section 3, the one-shot operation cementing.
Every single primary cement job relies on some incredibly elegant cement plug logic. Before you pump the cement, you drop the bottom plug. As you can see, this one is hollow with a little ruptured disc inside. It wipes the drilling mud off the casing wall, it lands, and then it bursts open so the cement can actually flow right through it. Then, right behind the cement, you drop the top plug. This one is completely solid. Its job is to separate the cement from the displacement fluid that's pushing it down. When it finally lands on the bottom plug, it stops the flow dead in its tracks.
But because that top plug is totally solid, you have to know exactly when it lands. And this is exactly where your displacement volume calculation comes into play. The casing's internal capacity, measured from the surface all the way down to the flow collar, is your absolute stop signal. Knowing this exact volume in advance isn't just some fun geometry exercise, it's quite literally how you know when to stop your pumps. If you don't, you risk pushing all your cement right out the bottom and leaving yourself with a disastrous wet chute.
Now I want to pose a scenario for you, because this creates some incredible tension on the rig floor. Imagine you have pumped the exact calculated displacement volume we just talked about, but you didn't see that sharp pressure spike at the surface that tells you the top plug actually landed, what we call the plug bump. So what do? Do you just keep pumping and pushing until you feel it?
The answer is a rock-solid hard rule: stop. Do not chase it. You have got to trust the calculated volume over that nagging gut feeling that maybe just one more barrel of fluid will fix the job. If that plug didn't bump, something in your model is wrong. Maybe a plug didn't actually release, or maybe there's a leak somewhere. But if you keep pumping, you are absolutely going to overdisplace the cement right past the chute and destroy the bottom of your well. You have to trust the math.
And hey, if you do end up with a problem that requires remedial cementing, like a squeeze job, for example, there is another hard mathematical limit you have to respect. Your squeeze pressure must absolutely stay below the formation fracture pressure. If you exceed this calculated limit, you will literally break apart the exact rock you were trying to seal. Like we keep saying, everything out here is bound by these numbers.
Okay, let's wrap things up with Section 4, rig rhythms and crucial datums. Truly understanding conventional drilling means you have to understand the Kelly drilling rhythm. The typical rhythm is usually about 30 feet of hole drilled per Kelly down, which is then immediately followed by a full connection cycle to add the next joint of pipe to the string. And it's fascinating because even the physical shape of the Kelly is a strict geometric calculation. You can have a square Kelly with 4 faces, sure, but a hex Kelly with 6 faces is very often selected instead. Why? Because that specific geometry spreads the rotational torque much, much better across the bushing.
And speaking of that connection cycle, actually making up a connection on the rig floor involves 2 very distinct mathematical and mechanical phases. First up is the spin phase. Using a spinner or a spinning chain, this involves many turns at a high speed but virtually zero torque. Once those threads are fully together, you move right into the tongs phase. This is the exact opposite. You are applying massive, huge torque, which is strictly dictated by API tables, by the way, over just a tiny fraction of a single turn to perfectly seal that rotary shouldered connection. Now, as we drill joint after joint, deeper and deeper, we have to know exactly where we are in the earth. That brings us to a highly essential depth datum, TVDSS, or True Vertical Depth Subsea. Because drilling rigs sit at all sorts of wildly different elevations, you need a universal baseline to make sense of anything. TVDSS equals the depth below the Kelly bushing minus the Kelly bushing's own elevation above sea level. Every single depth quoted for a well, from the geology reports to the engineering specs, anchors right back to this one fundamental calculation.
So, as we wrap up this explainer, I want to leave you with a bit of a provocative thought. We've just seen how a simple displacement volume dictates an entire cement job, how specific gravity predicts a completely invisible lethal gas hazard, and how kill sheets safely control bottom hole pressures.
If a single calculation error can sink H2S into a cellar or shatter a well with excess pressure, are you trusting your math on the rig floor, or are you just trusting your luck? Understanding these figures isn't just about passing a test. It is the literal foundation of every safe operation out there. I really hope this structured look at these formulas has sparked your curiosity to dive even deeper into the source material. Thank you so much for joining me today.